studying. Yeah, I live.
I woke up the other night, my blood just froze. I dreamt I took the SATs without no clothes. Oh, I got SAT blues. I got everything to lose. I got SAT blues. I got everything to. Don't wanna stay up all night reading the dictionary. Words I just don't understand. I opened up the test booklet. I let out a shriek, 'cause half the questions were written in Latin and Greek. Oh, I got SAT blues. We got everything to lose. I got SAT blues. I got everything to. What do I do with these fractions? I can't figure this equation out. The numbers keep spinning round. I don't know a hypotenuse, a isosceles triangle. It turns me upside down. Oh, I got SAT blues. We got everything to lose. I got SAT blues. We got everything to. SAT blues. We got everything to lose. SAT blues. We got everything to.
That's SAT Blues, the new hit single by PTD and the Students. And for all you juniors and seniors out there singing the SAT Blues tonight, don't you worry, because we're going to dedicate this whole show to you.
Good evening, and welcome to the Castle Integer here in the land of odd and even. My name is... But who I am and what I am are not important. What is important here in the castle is you. You and... mathematics. Does that scare you, mathematics? It shouldn't, you know. Math is really quite simple. Especially the kind you use to dig up answers in that dreary thing you mortals do, the scholastic aptitude test. So simple. All you need to do is remember the things you've known for year after dusty year. Addition, subtraction, fractions, percentages, basic earthly arithmetic concepts like that. There's nothing to fear. Sounds too simple, does it? Think you know it all? Well, beware. Overconfidence is like the cobwebs of this castle. They will blind you and deceive you so that you'll stumble into the ghastly clutches of error. Did I frighten you? 1,000 pardons. I only mean to warn you. It is true. You should never fear the math of the SAT, but there are demons lurking in the shadows. Demons that will try to trick you and confuse you and make you abandon what is right. These demons must never be left untamed. But trust me, armed with only the torch of good sense and practice, you shall contain these demons. Hark, the hour grows late. Come, come with me now, and I will show you how to use the simple building blocks of your own knowledge to vanquish these demons lurking in the darkness. Shed a bit of light on these demons, and you can see they are nothing more than numbers, the basic building blocks of arithmetic. You think you know all about numbers, Well, beware. Know all the names they go by. Learn to recognize them instantly before they trick and trap you. An integer is another name for whole number, not a fraction. Anything from 1 to, well, 1 million and beyond. Personally, my favorite integer is 13. There are positive integers and negative integers. Zero is an integer, but it is neither positive nor negative. On the SAT, you may see a number line with 0 in the center. Note that the positive numbers grow bigger as they move right from the 0. Negative numbers grow smaller as they move left from 0. For example, -8 is smaller than -3. Be sure you know the rules for working with signed numbers. When adding numbers with different signs, subtract the smaller number, not counting the sign, from the larger number and use the sign of the larger number. With subtraction, change the sign of the bottom number and add the two numbers following the rules for addition. And remember the rules for multiplying with signed numbers. When the signs are the same, the product will always be positive. When the signs are different, the product will always be negative. For division, when the signs are the same, the quotient is a positive number. When the signs are different, the quotient is a negative number. And never forget the odd and even behavior of numbers. See what happens when you add two even numbers, or two odd numbers, or an even or an odd. See what happens when you multiply in these various combinations. Even numbers can be evenly divided by 2, that is, with no remainder. Odd numbers cannot. You will always have a remainder of 1. You will thus always have a quotient that is a whole number plus the fraction 1/2. Recognize that the longest of even numbers will always end in an even number, and the longest of odd numbers will always end in an odd number. And you should know about consecutive integers and how to express consecutive integers in terms of a variable. Consecutive integers are numbers that follow each other, such as 3, 4, 5, 6, or 45, 46, 47, or 48. If you don't know the first number, you can call it n. Then the series would be expressed as n, n plus 1, n plus 2, n plus 3, and so on. And do you know what prime numbers are? Yes, here they are. Silence. A prime number is any number that cannot be divided by any other number but 1 and itself. These are prime numbers. 2, 3, 5, 7, 13, 17, 19. All integers are made up of digits. There are, of course, 10 of them. For instance, the number 1,234 contains 4 digits. Remember this. The SAT does ask questions that require you to know these things cold. And now, do you recall what you do with these numbers? The basic operations of arithmetic? You add, multiply, subtract, and divide them, of course. Simple, yes? Of course. Until you become careless and make mistakes that cost you valuable points. Mistakes such as these. Failing to remember what the results of the 4 basic operations are called. Addition yields a sum or total. Subtraction yields a difference. Multiplication yields a product. And division yields a quotient. Know these terms. Do not waste time on the test trying to remember when a question calls for the sum of two numbers or the product of two numbers. And now, on to those fractions. Fractious, a word you should note. Peevish, unruly. But don't worry, they can be tamed. Fractions, or I should say proper fractions, are numbers less than 1. The number above the line is called the numerator. The number below the line, the denominator. A fraction can also be expressed in terms of division. The fraction 1/2 also means 1 divided by 2. To add and subtract fractions, they must have the same or common denominator. You simply add up the numerators and place the sum over the common denominator, or subtract the numerators and place the difference over the denominator. If they do not have a common denominator, you must find one. This will be the lowest number that can be evenly divided by each denominator of the numbers you have to add or subtract. To change each fraction, you divide the common denominator by the given denominator and multiply the quotient by the given numerator. Our illustration should make this clear. Notice that the value of each of the fractions remains the same as it was. Multiplication is really quite simple. To multiply fractions, you multiply the numerators and put that product over the product of the denominators. Remember that most problems involving fractions on the SAT will want you to put the answers in their reduced form. If, after multiplying or adding, you get a large, unwieldy fraction, you can simply reduce it down to size. Just find the highest factor that is common to both the numerator and the denominator, and then eliminate them, that is, cancel them out. Cancellation can be used to make operations with fractions easier, to eliminate having to multiply or divide huge numbers.
When dividing fractions, never forget this essential first step. Invert the divisor, that's the second fraction, and then follow the procedure for multiplication.
Remember these devils? Mixed numbers. A whole number and a fraction. Be sure you know how to convert them into what we call improper fractions, that is, fractions with a value of 1 or greater. One way to do so is multiply the integer by the denominator and add the product to the numerator of the fraction. In this manner, it is easy to see that 3 and 1/2 become 7/2, or 7/2. Fractions? They seem so small, so inconsequential. But please bear in mind that so many of the problems on the SAT require you to be able to handle them with ease, to reduce them as far as they can be reduced, to convert mixed fractions, to know how to compare them. You will be asked to determine which is the larger of two fractions, or to know which is the largest of several. Don't be misled by fractions with seemingly big numbers. Fractions such as this. You must realize that this little fraction, or what appears to be a little fraction, is far greater in value than the one with all the digits. That little sideways v means greater than, in case you forgot. And bear in mind that when you multiply proper fractions, the product is lesser in value than the two factors. Look before you leap to answers that look good at the first glance. And finally, pay attention to these special kinds of fractions, those with denominators of 10 or multiples of 10. Know that you can easily convert them to decimals. Silence! I said decimals, not decibels, demonic dummies. Indeed, decimals are just another way of illustrating fractions. In fact, all fractions can be converted to decimals simply by dividing the denominator into the numerator. When the denominator is 10, or 100, or any multiple of 10, the task is easy. Simply place the decimal point in the proper place in the numerator. 6/10 becomes decimal point 6. 60/100 is exactly the same, and so is 600/1000. But to convert 6/100, you must place a 0 after the decimal point in front of the 6. Note that the decimal point serves a very special purpose. Its placement tells you the value of the number. Let's see what happens to the value when we move the 6 in relationship to the decimal point. The farther to the right the 6 goes, the smaller its value becomes. And why is this infinitesimal little dot so important? Let's try this exercise. Take this number and place a decimal point anywhere you choose. Can't decide? Well, suppose the decimal point determines the amount of money you should be rewarded for demolishing these demons. Or suppose it determines the number of hours you will be required to spend in this daunting dungeon, Where shall you place the decimal point then? As you can see, in the same series of digits, the farther right the decimal point goes, the greater the value. The farther the left, the lower the value.
And perhaps more to the decimal point. Your understanding of these fine points will make your tasks on the SAT so much easier. For no doubt, you will encounter a problem which asks you to compare two decimals.
When adding and subtracting again, be sure to line up the numbers in the right columns. You laugh. Many points have been stolen by the decimal demons. The way to keep them in their place is simply that. Be sure to keep them in their proper place. When multiplying numbers with decimals, you must keep track of the number of digits to the right of the decimal point. Count them up and place the decimal point that many places to the left of the last number of the product. To divide a decimal into another number, you must banish the decimal point in the divisor. Move the decimal point over so that the divisor is a whole number, and then move the decimal point over the same exact number of spaces in the dividend.
Listen, the demons are growing quieter. Good. We are about 75% done. Percentages. Just a little matter of hundreds, eh? Remember your root words from the verbal part of the test? Percent, cent, meaning hundreds. Remember? Well, you will now. Percentages, it seems, are often converted into and out of many things, like decimals. Indeed, a percent is another way of expressing a decimal.
To convert a decimal to a percentage, simply move the decimal point 2 places to the right and add a percent sign. This conversion procedure can work in reverse. Make a percentage into a decimal by removing the percentage sign and placing a decimal 2 points to the left.
Decimals and percentages are easily transformed into fractions, with or without a full moon. It's just a matter of moving the decimal point 2 spaces to the right, or remove the percentage sign and place the numbers over 100. See how 0.60 becomes 60%, which can then become 60 over 100? Do you find 60 over 100 too unwieldy? Notice you can then reduce the fraction to 6 over 10, or even further, to 3 over 5. Converting fractions to percentages is a touch trickier.
Don't mind them. They know they are doomed. Let's say 3/4 equals what percent? Again, my friend, it's hundreds. So just place the unknown what over 100. Call the unknown x for easy handling. And surely you know what to do now. 3/4 equals x over 100. That makes 3 over 4 times 100%, which equals 75%.
I must hurry. Dawn approaches. But there is one more arithmetic demon for you to silence, perhaps the trickiest of them all. Averages. You know all about averaging, finding the average set of numbers by totaling the numbers and dividing by the number of numbers. The formula for finding an average is average equals the sum total of whatevers over the number of whatevers. Confusing? Let's illustrate by way of an example.
What is the average of these 3 numbers? 4, 6, 11. You add up the numbers and divide them by 3, which is how many numbers there are. 21 divided by 3 equals 7. Simple?
Yes, but beware these common pitfalls. Many guests to the castle, guests just like you, forget to find the total number of whatevers before adding the numbers up, and many forget to add up all of the numbers.
For example, suppose Bob the vampire bit 2 people in one night, 3 people each of the next 2 nights, and 5 people on the 4th night. How many numbers do you have to add up?
Silence, demons! Do not listen to them.
This answer is incorrect. The total number of nights is 4, not 3.
a fortnight.
This is wrong too. It's the total number of bites divided by the total number of nights. Remember, Bob bit 2 people one night, 3 people one night, 3 people another night, and 5 people another night. That's a total of 13 people, a very telling number, in 4 nights. Now, a few more tricks about averaging. In many averaging problems, you may be presented with only partial information. If you are told, for example, that the average number of demons found in a haunted castle is 75, and that 30% of the haunted castles have an average of 65 demons, what would the average number of demons found in the remaining 70% of the haunted castles be? How many haunted castles are there? You don't know. So you have to pick a number that's easy to work with, say 10. The total number of demons in all of the castles is 10 times 75, or 750. 30% of 10 castles is 3. You know that 3 castles has an average of 65 demons each. So the total number in these castles is 3 times 65, or 195. The remaining 70%, or 7 castles, must have a total number of demons equal to 750 minus 195, which equals 555. The average number of demons in this group of castles is 555 divided by 7, or... Don't panic when you see tricky problems like this. Relax and think of the simple points we provided here today at Castle Integer. There, that wasn't so hard. There's nothing to be afraid of if you remember your basic building blocks and use them carefully. Don't take them for granted. If you are careless with but one small decimal point, you too may become lost in the endless night. Fear not the demons of math. They will only get out if you let them. And now, my friends, we must part. Your way is to the light, and mine. Farewell.
We got everything to lose. SAT blues. We got everything to lose.
Hello, music fans the world over. This is Jimmy J speaking to you from our studio in downtown Springfield. This is the day that you've all been waiting for, our live telecast, Math Aid, the benefit show for all you kids out there preparing for the Scholastic Aptitude Tests. As you know, dozens of the top recording artists in the world of pop music have donated their time and talent to this extraordinary event. Via our satellite feed, we'll be taking you live to locations all over the world to interview artists like
Nigel McGuffin of the Constants, Felix Funk and his Funky Functions, Rivers and the Radicals, Casey Cube and the Exponents, that fabulous doo-wop group, Linus and the Equations, and Miss Polynomial, and of course my co-host, the granddaddy of country music, Johnny B. Squared.
But don't go away, because we'll be right back with Math Aid.
I got a taste for one with the juice. I want the orange that turns and loose. We got a thirst for something cool and light. All we need is mandarin orange slice. With 10% juice, we got the juice. It's the #1 twist. We got the taste, number 1 miss. We got the juice. Diet too. Slice, slice.
Hi, Jimmy J here, back with Math Aid. This segment of the show will be dedicated to algebra. In case you didn't know it, about 1/3 of the math sections on the SAT involve algebra, so that makes it very important to know how to solve algebraic equations. With me as co-host is someone who obviously knows the formula for musical hits, Mr. Johnny B. Squared. Good to have you here, Johnny B.
Well, Jimmy J, it's great to be here.
Now, we're here to help kids preparing for the SAT, so let's get right down to business. We'll start with the basics. What are the first things the kids should know about the algebra on the SAT?
Well, you know, Jimmy, algebra is a lot like music, whether it be country music, rock, rhythm or blues, what have you. See, if you know some basic chords and tempos and musical patterns, well, you can write and play as many as 100 different tunes. See, in algebra, it's the same way. If you know the basic rules and principles and shortcuts, you can solve just about any algebraic problem that comes up.
So, how can they learn some tricks to help them do that?
Well, first, we want to give the kids some concepts to remember. Now, let's say you have something like this. That's an equation. I'm sure you all know that. Now, if you want to make a sentence out of that equation, you have 2x plus 3y equal 12. Now, in an equation, you have terms instead of words. So in this equation, 2x is a term. So whenever you're talking about math, you got to know what the word term means.
I see. So then 3y is a term. Is 12 a term?
Oh, that's right. 12 is a term. Now, the numbers in front of the letters in each of the terms are called coefficients. So 2 is a coefficient for x, and 3 is a coefficient for y. Now, an expression is a combination of terms and mathematical operations. So 2x plus 3y is what mathematicians call an expression. And if you have an expression with 2 or more terms, that's what we call a polynomial.
And what better way to introduce our very special guest, Johnny B's lovely daughter and one of country music's hottest new singing talents, Miss Polynomial. Come on out, Polly.
Hey, baby.
Hi.
2
minus 1 equals 7.
Take it, baby.
Yes, 2 minus 1 equals 7. Hello, Daddy.
Hey, baby.
Hello, Jimmy J.
Well, hello, Polly. I bet your daddy is just thrilled about your new song, 2 minus 1 equals sad.
Oh, he is, Jimmy J. Of course, without Daddy, I couldn't have done it.
Baby.
I know just what you mean, Polly. I know I couldn't have done this very special benefit without the help of Johnny B Squared and all our guests. Now, we've got a lot to cover, so let's get back to the task at hand here. Polly's going to help explain how to work with these expressions.
That's right. Now, I'm sure most of our fans know this stuff, but it's important to keep these ideas in mind as we go along. Now, on the SAT, sometimes they'll give you a problem that asks you to evaluate a certain expression, see? Now, by evaluate, they mean just to substitute numbers for the letters and then add, subtract, multiply, or divide to come up with a number.
For example, what is the value of 2D if D equals 3? You just plug in the number 3, multiply, and get 6.
That sounds easy enough.
Well, it is, JJ, but when some kids see something like this...
They get all panicked and don't know what to do.
Well, now there are a lot of ways to approach this problem. Some kids will first try to figure out what x equals. Well, that's simple. If 3x equals 1, then x must equal 1/3.
Now, you try to put that fraction in the equation, and you find out you have to deal with more fractions. And that's where lots of little errors in calculation begin.
The easy way around this is to remember that 3x equals 1. So you start by just substituting 1 for 3x. What do you do with the 9x? It's easy to see that that's just 3 times 3x, or 3 times 1, or just 3. Then you just put in a 1 for the other 3x and do the calculation.
So now you have 3 plus the expression in parentheses, which is 1 minus 4 squared. That becomes 3 plus minus 3 squared. Finally, you have 3 plus 9, which equals 12.
So kids taking a test should remember to look for shortcuts before jumping in to solve the problem in the usual ways.
Well, you two make it sound so easy.
Well, it's not very hard. Just like with music, you gotta practice to make it second nature.
As I was watching Polly solve that last equation, I kept wondering, how do you remember which of those steps to do first? To answer that question, we're going to take you across the Atlantic Ocean to the UK, where my counterpart over there, Jock Wellington Jones, is standing by with Nigel McGuffin of the Constants.
Thanks, Jimmy. Jock Wellington Jones here, and hello to all our good friends in the US of A. A catchy little tune, eh? I have with me the lead singer of the very, very famous group who sings it, Nigel McGuffin of the Constants.
Hello, Jock. Glad to be here.
Good. Well, now you promised you'd answer the musical question that's been on everybody's mind these days, and that is, what in the name of the Queen, God bless her, does the song mean?
Well, you see, we've got this drummer Rocco, see? And he's got this crazy aunt. And whenever she comes in, she starts spouting mathematical formulas and equations, you know, things like that. She just kind of blurts them out like.
Quite a cheeky little habit, I should say.
Yeah, it is. You know, in fact, a couple of months ago, we were in the studio, and she come in and starts going on, you know, with x squared plus 2y equals 64. That's when Rocco started apologizing. He went, "Hey, please excuse my dear Aunt Sally." Well, you've got to admit, it was a bit strange her going on like that.
I should say.
Well, naturally, we wrote a song about it. In fact, if you listen really close to the record, you can hear Aunt Sally in the background there.
You mean those high-pitched vocals are actually Aunt Sally singing mathematical equations?
That's exactly right. That little trill sound is really Aunt Sally singing x squared plus 2y equals 64. You know, played through a ring modulator and recorded at double speed. We thought it was quite a nice effect, Dad.
I think he's putting us on. That's a charming story about Rocco's Aunt Sally, but the word is that the line, "Please excuse my dear Aunt Sally," has some hidden significance that would be of tremendous help to all our audience, all those kids studying for the SATs.
Yeah, well, that's right. See, the first letter of each word, "Please excuse my dear Aunt Sally," makes up the initials P, E, M, D, A, S, which stands for parentheses, exponents, multiplication, division, addition, and subtraction. Now, when you're trying to figure out mathematical equations and expressions, you have to perform the operations in the correct order. Otherwise, you'll get all bunged up. Well, I've worked out a little example for you. Let's say I have a problem like this. If x equals 2, y equals 6, and z equals 8, what is the value of 3x squared plus 4 over 3 times y minus, parentheses, 2z minus 5, close parentheses, eh?
I have no idea.
Well, mate, all you have to do is remember our little song. I've got a video to show the kids how it works.
Well, let's have a look.
And Sally comes walking in the room. At first she says,
Parentheses, parentheses, always start with these. Parentheses, parentheses, it's really quite a breeze.
Whatever does she mean, if you please?
Parentheses, parentheses, always start with these. Parentheses, parentheses, it's really quite a breeze.
I don't understand this.
If you please, excuse my dear Aunt Sally. Please, 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 excuse my dear Aunt Sally. Please excuse her, but never lose her, oh please. Excuse my dear Aunt Sally.
and then she says,
It takes a few moments to handle those exponents, those little 2s and 3s. It takes a few moments to handle those exponents, those little 2s and 3s.
I don't know what she's talking about.
If you please, excuse my dear Aunt Sally. Please, 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 excuse my dear Aunt Sally. Please excuse her, but don't confuse her, oh please. Excuse my dear Aunt Sally.
oh, now here she comes again.
First multiply and then divide, add and then subtract. It's as easy as the ABCs.
Whatever is this that she means?
First multiply, then divide, add, then subtract. It's as easy as the ABCs.
Who ordered the shrimp? I ate it.
If you please, excuse my dear Aunt Sally. Sally. Excuse my dear Aunt Sally. Excuse my dear Aunt Sally.
Do I have to know this?
Well, I'm impressed with your algebraic skill, Nigel, and I'm sure it will be of a big help to all your fans in the US of A, planning to go to university.
Well, if they remember our song as they're taking the test, it might help them to get a better score.
I'm sure they will. Cheers, and good to see you again, Nigel.
Ta, Governor.
Meanwhile, home viewers, we're going to give you a chance to put the song Please Excuse My Dear Aunt Sally to the test.
If you please.
We're back live from our studio, and I'm talking with Johnny B. Squared. Loved that Please Excuse My Dear Aunt Sally.
That's a real humdinger of a song for this benefit.
So what do we do to add to what we've learned so far?
Well, JJ, every school kid learns a little trick called factoring, and it's one of the most important things to remember for the algebra problems on the SAT. A factor, remember, is one of two or more numbers which, when you multiply them, give you a product. So factoring is where you sort of separate an expression into its factors. Now, if you come across something like this, you know you can change it into this.
Johnny B., I'm great with words, but not with numbers. So maybe you could help me explain how that works.
Okay, Jimmy, sure. Now, the expression x squared plus 2x has the term x on both sides of the plus sign. So we can factor out the x and put what remains in parentheses. And you can also go the other way around. So if you have x times x plus 2, you can multiply through by x to get x squared plus 2x.
Now, what would you call that? Unfactoring?
Well, sure, I guess you could, Jimmy. Whatever helps the kids to remember what they need to know for the test. Now, most kids taking the SAT know how to factor. But the trick is this. On the SAT, when you come across a problem that could be factored, you go ahead and factor it, because more than likely it'll help you get the answer quicker. And here's a good example of the kind of factoring problem found on the SAT. Factor out that y and you get this. But if you come across a problem with expressions that could be unfactored, to use your word, Jimmy, then you go ahead and do so. Once again, that should help you find the answer quicker. So suppose you get this problem, and you get these choices.
Well, I guess you would unfactor.
That's right. And you'd get negative 3a plus 3b. Then you would factor again to get 3 times b minus a.
Well, maybe the kids watching will get the hang of it.
And now, live from a studio somewhere on Main Street, USA, Linus and the Equations. Ready, Linus?
Cut! Cut! Where's Linus? Where's Linus? Linus didn't show. He didn't. Roll something. Go to a commercial. Anything. What is this? What is a child doing on the set? Who is this kid? What do you want?
Is this where they do that math aid show?
Yes. We're really busy, kid. Can you go play?
I'm Linus. And these are my equations. I'm supposed to do something on equations.
Linus and the Equations are a doo-wop group.
What's a doo-wop group? I don't know anything about doo-wop groups. I'm just a kid. A very gifted kid. I know all about linear equations and quadratic equations. You want to see my act?
Well, okay. Go for it. Do it.
Okay. Here goes. Well, first you have to know what an equation is, okay? An equation is like a balancing act. All the things on the left side have to equal all the things on the right side. Over here, I have 3 x blocks and 5 y blocks. And on the right side, I have 4 x blocks and 2 y blocks. That's an equation. I can simplify real easy. Watch. I take the 3 x blocks from this side, so I have to take 3 x blocks from the other side. Now I have 5 y blocks on one side, and that's equal to 1 x block and 2 y blocks on the other side. You can simplify this again. I take 2 y blocks from the left side and 2 y blocks from the right side. And that leaves 3 y blocks equals 1 x block.
That's great, kid. What a wonderful kid. What a beautiful kid.
Wait!
Yes.
Wait. That's just the baby stuff. I haven't finished. I have a little play to show you how to solve linear equations. It's called How to Find X, the Unknown. Linus presents X, the Unknown, starring X for Math Aid. Now this looks like a bunch of blocks, but it's really a linear equation. J equals xk over m plus x. We've got to find x, the unknown. How do we do it? Easy, as long as you follow the rules for solving linear equations. Rule number 1. If there are fractions or decimals in the equation, remove them by the use of multiplication. Well, we don't have any decimals, but we do have a fraction. So, we get rid of it by multiplying both sides by the expression m plus x. And now we have this. Look. See, we also moved one of the x's over to the other side. And we had to put the expression m plus x in parentheses. Rule number 2. Expand any expressions enclosed in parentheses. Now we multiply j times the expression in the parentheses. So we get jm plus jx equals xk. Rule number 3. Collect all terms containing the unknown on one side of the equation. See? We have an x block on the left and one on the right. So, we subtract the term jx from both sides. We take it away from here and move it over to the right. And don't forget to add the negative sign. Rule number 4. When terms cannot be combined, find the coefficient by factoring. See? Here's how we find x. We factor out the x from the expression xk minus jx. So we have jm equals x times k minus j. Now we're ready for the last step. Rule number 5. Once you've found the coefficient, divide both sides by the coefficient. So, we divide the left side by k minus j, and the right side by k minus j. And here's what we get. Hey, we found x, the unknown. Jm over k minus j equals x. Simple!
That was beautiful. What a kid. What a kid.
Oh, hey, yo. Gee, I'm here, finally. I got caught in traffic. Sorry I'm late. And you know, I have no idea what those equations are.
Well, Linus, it looks like you've been replaced.
What? Who's this kid?
Well, he says his name is Linus, and he does a bit about equations. He just did something on linear equations, which is very cute.
Right. Yeah, well, I'm here to take over now, and I got something to say about quadratic equations.
I know all about those.
You ready? All right, you know, I'm going to tell you a few things about quadratic expressions and equations. You know, quadratic equations may look scary, but they don't have to be. To prepare for the SATs, there are just a few things you have to know about quadratic expressions and equations. Like, whenever you see something like this, x squared minus y squared, just remember, that's a quadratic expression that can be factored into this, x plus y times x minus y. And here's another quadratic equation you're often going to see on the SATs. X squared plus 2xy plus y squared. This expression can be factored like so. x squared plus 2xy plus y squared equals x plus y times x plus y, which equals x plus y squared. So, what's the big deal with these quadratic expressions and equations? Well, I don't even really know why they have them, but I do know that...
I know what they're for.
Yo, kid, you had your turn, okay? Like I was saying, I do know that they come in handy on the SAT tests. Like, for instance, here's one of the problems they had on an SAT. If x plus 3 squared equals x minus 3 squared, then x equals what? A, 0, B, 1, C, 3, D, 6, or E, 9. You could start putting all the different answers in and come up with the right answer that way, but if you remember quadratic equations, you could unfactor both sides of the equation kind of like this. X plus 3 times x plus 3, which equals x squared plus 6x plus 9, and x plus 3 times x minus 3, which equals x squared minus 6x plus 9. Now you have this. X squared plus 6x plus 9 equals x squared minus 6x plus 9. Now it's easy. Just take out the terms that are the same on both sides of the equation, and you're left with this. 6x equals negative 6x, or x equals negative x, or x equals 0. See? So the answer is A, 0. Okay, you didn't think that was such a big deal, huh? Well, then look at this one. Here's another problem you're going to find in the SATs. 45 squared plus 2 times 45 times 55 plus 55 squared equals what? A, 5,050, B, 9,100, C, 9,900, D, 10,000, or E, 14,950. Hey, who wants to do all that multiplying, huh? Not me, no way. You don't have to either, as long as you remember this stuff about quadratic equations. Remember before when I showed you this quadratic expression, x squared plus 2xy plus y squared? Does that look familiar or what? Of course. Look, see, this problem is the same thing as this expression, so all you gotta do is what? That's right, factor. And you get this. 45 plus 55 times 45 plus 55, which equals 100 times 100, or 10,000. Piece of cake, right? Of course. The answer is D, and that is the truth. Hey, let me see that thing. You gotta keep this thing in tune, you know. It's gonna be a performer.
That was great. Mwah! Back to you, Jimmy. Roll it.
That's SAT Blues. And I hope our rock special can help you cure your SAT blues. Johnny B, I want to show the viewers something that I'm sure everyone will recognize. That distinctive signature of yours. It reminds me of one of the things in math that always trips me up. Exponents.
Exponents. That's right, Jimmy. You gotta know how to work with these. In fact, I just did an album with Casey Cube and the exponents, and it just went gold. We called it B squared plus C cubed equals power.
That's another winner, Johnny B. Let's see if we can talk to Casey now, standing by in a studio on the West Coast. Casey?
Hey, I hear you, Jimmy. I've been watching the show. It's great.
Now, what can you tell the kids out there about exponents?
Exponents are like shorthand. You take b squared, for instance. Most kids know that that means b to the second power, or b times b. So, if b were 2, it would be 2 times 2, or 4. Now, c cubed is c to the third power, or c times c times c. If c were 3, that would be 3 cubed, or 3 times 3 times 3, which equals 27. That's the easy part. Now, here's the tricky part. What do you do with this? b squared times b cubed equals what? Well, if you write it out, you see how it works. b times b times b times b times b equals what? So you can see that another way to write this is b to the 5th, or b to the 5th power. So if you see a similar problem on the SAT, you could apply this rule. When multiplying base numbers with exponents, you just add the exponents. In this case, 2 plus 3 equals 5. so it's b to the 5th. Now let's substitute a 2 for the b. 2 to the 5th power is 2 times 2 times 2 times 2 times 2, which equals 32.
Well, like, what if you have b squared plus b cubed? Addition.
Good question, Conrad. So let's try it. By substituting the number 2 for b. 2 squared equals 4, and 2 cubed equals 8. 8 plus 4 equals 12. But if you add the exponents, you get 2 to the 5th power, which we just saw was 32. Quite a difference, huh? So be very careful when you're doing these kinds of problems. Be sure to check if it's multiplication or addition. Only when it's multiplication do you add the exponents of the same base. Division is the reverse of multiplication. So, what do you think the rule is for dividing exponents with the same base?
You subtract the smaller exponent from the larger one.
That's right. Like b to the 5th divided by b squared would equal b cubed, which might also be shown like this. B to the 5th over b squared equals b cubed. To check it out, plug in a number. We'll use 2 again. 2 to the 5th over 2 squared equals 2 cubed, which equals 8. Or, another way to look at it, 2 times 2 times 2 times 2 times 2 over 2 times 2 equals 32 over 4, which also equals 8. Now don't forget, don't try to use the rule for division for an expression that involves subtraction. B to the 5th power minus b squared equals what? Substituting a 2 for b. 2 to the 5th power minus 2 squared equals 32 minus 4, which equals 28. Don't subtract the exponents. Now here's a tip for you as you're doing problems on the SAT. If you can't remember the rule for something, try substituting small numbers for the letters and see what you get. But when working with exponents, you have to remember a few other tricky points. When the exponent is even, as in b squared, the variable b will always have 2 values.
Ooh, now, how's that again?
Well, if you recall, Conrad, the rules for working with signed numbers, you know that multiplying 2 numbers with the same sign, both positive or both negative, you always get a positive product. So, for b squared, b could be either a positive or a negative number. As in 2 squared equals 4, or negative 2 squared equals 4. So, in a problem in which the result is b squared, b would equal positive or negative b. But this is not true for odd-numbered exponents. b equals 2 if b cubed equals 8, and b equals negative 2 if b cubed equals negative 8. Now here's some other tricks with exponents. So if you have a base number that is greater than 1, it always gives you a larger product. That's positive 2 squared equals 4. But if you have a fraction, the result will be a number smaller than the one squared or cubed. Be sure to use this information to help you eliminate answer choices on the SAT math sections. For example, if the problem is a quantitative comparison like this, which is greater, A or B, you know that a fraction with an exponent gives you a smaller value than the fraction itself. So, in this example, you can easily eliminate answers A and C. Well, Jimmy, that should give the kids a few pointers to help them earn some points on the SAT.
Thanks, Casey. And we're about to take you to Chicago to hear from Rip Roots and his Radicals. Not many fans know that Rip and all the members of the band have high math aptitudes. And between sessions, they like to hang out and argue the fine points of math. No, really. So we're going to eavesdrop on them as they debate what you need to know about, well, the obvious, roots and radicals. First, let's say hello to Rip. Rip?
Yeah? Oh, I hear you, Jimmy.
Hey.
Hey!
all right. Hey, this Math 8 thing isn't exactly like Woodstock, but I can dig it, you know? I mean,
All right.
these kids today, they really want to go to college.
Far out.
That's hip.
Glad you joined us for Math Aid, Rip. So with no further ado, we'll just sit back and let you guys do your thing.
All right, okay, now here goes. Now, whenever you see this radical sign, like this right here, you know they want you to find the square root of the number that's under the sign.
Yeah.
Like, square root of, like, a square root of 25 is 5. It's like the opposite of 5 squared.
Ooh.
Peace, man.
Yeah.
You with me so far, Radical?
Yeah, man, far out.
Okay, now for the SAT, there's just a few things that you gotta know about radicals, all right? First, you can only add and subtract radicals if they are exactly the same.
That's right.
Now, let's say that you have this, okay?
Oh, yeah, man.
Oh, man, that's easy, man. You add 3 plus 4 to get 7 radical 2.
Oh, groovy.
Okay, or if the problem was this, hey, the answer would just be the radical of 2.
Oh, that's easy, man.
Come on, give us something harder, man.
Yeah.
Okay, all right, guys, all right. Then what do you do with this? Oh, sorry. Okay.
Oh, yeah, yeah.
Oh, yeah. See, now that can't be done, man. You can't add radicals that are different.
Of course you can. You just have to figure out the square roots and then add.
Oh. Yeah, well, that would take a lot of time. And besides, they don't ask you things like that on the SAT.
Whoa, man. What if they ask if 4 radical 2 is more or less than something like, say, radical 7?
Lighten 'em up, guys. Okay. It's true, you're not expected to do a lot of time-consuming figuring, but it helps to have a sense of radicals that aren't perfect square roots.
Right on, you're right.
So that you can make educated guesses.
Yeah.
Now, here's something that I used on the SATs myself. A long time ago, but it still works today.
Yeah.
Now, you know that the square root of 1 is 1, and the square root of 4 is 2, and the square root of 9 is 3. So you make this little number line like this.
Far out.
Right, man. That's all right.
Now, you can figure the square root of 2 and the square root of 3 are between numbers 1 and 2. And the square roots of 5, 6, 7, and 8 are between the numbers 2 and 3, and so on. I don't want to write on the piano. Okay. Now, with this, you can make calculated guesses without having to do the long calculations.
Yeah, all right, okay, that's cool. So, now, you can see that the square root of 2 is maybe not quite 1.5.
Right.
And the square root of 7 is probably a little over 2.6.
Okay, dude.
So, 4 times radical 2 is definitely greater than radical 7.
Right on. Yeah, far out. Okay.
Can I go on now?
Oh, yeah,
man.
yeah, sure. Yeah.
Go ahead.
All right, there's another way to deal with adding radicals that aren't the same. Now, say you have this.
Uh-huh.
Now what do you do?
You can't use your little number line idea because these numbers are too high.
Yeah, so you like have to factor out any perfect squares.
Yeah, definitely, man. Gotta get rid of the square.
Right on. Right. So what you do is you divide both numbers by, let's see, 3 goes into them both, so you'd have this. Okay, so you factor out the 2 perfect square roots, and now you can add them.
Yeah.
You should remember this to simplify big numbers under radicals in general. Like make radical 40 into radical 10 times radical 4, or 2 times radical 10. Yeah. What about multiplying and dividing with radicals? The rules are you just multiply the numbers both outside and inside the radical. So, radical x times radical y equals radical xy.
I'm hip.
Or, ready for this? 2 radical x times 3 radical y equals 6 radical xy.
Right on. And to divide, you just divide the numbers inside and outside the radicals. I mean, like radical x divided by radical y equals radical x over y. So, 10 radical x divided by 5 radical y equals 2 radical x over y.
Beautiful, beautiful.
Yeah.
Now, if the kids remember some of these rules about radicals...
Hey, wait, man. Rules
about radicals? Now, isn't that like a contradiction of terms?
Yeah, man.
Hey, come on, man. We're trying to help these kids taking the SATs. Don't bum us out.
He's right, dude.
Anyway, if they remember these rules and tips, they should have no problem with problems involving radicals.
No hassle.
Great. Thanks, Rip, and the radicals, too. Well, Johnny B., we're coming close to the end of Math Aid. Anything else you want to add before we hear from Felix Funk?
Well, Jimmy, there's one more little point, and that's how to work with inequalities. Now, we've been talking about equations where one side equals the other side. Well, in inequalities, one side does not equal the other side. Now, these are the various kinds of inequalities. This side means not equal to. This side means greater than. This side means less than. This side means greater than or equal to. And this side means less than or equal to. Now, the SAT test has these symbols right at the top of the page for every math section. But it's a good idea to know them ahead of time so you don't waste time on the test. Inequality statements are solved the same way as equations, but you've got to remember that when you multiply or divide by a negative number, you have to reverse the inequality sign. For this statement, you are asked to find the value of x. Start by moving the 9 to the other side of the statement, and of course you have to change it to a -9. Now, you divide by -3, and don't forget to reverse that inequality sign.
How do you remember which sign means greater and which means lesser?
Well, Jimmy, that's a piece of cake, because the sign always points toward the smaller quantity.
Ah, I get it. Thanks, Johnny B., for all those terrific tips. Felix Funk has a special message for you.
Hey, Felix Funk here, bringing you the latest lowdown on funky functions. Functions, man. Remember in math class when you learned about functions? You know, functions. That's another one of the way mathematicians save time. Save on ink, too. And you know those mathematicians, like, they don't waste a lot of words. They use signs and symbols, man, like, we say 2 plus 2 equals 4. Well, they say 2 plus 2 equals 4. Now, functions, now they work like this. F. Now, that stands for functions. Fx means, in this situation, 3 times x squared. So, if x equals 4, then fx would be f4, and that would be 3 times 4 squared. Now, that's 3 times 16, which equals 48. Get it? Now, let me give you a little example from music now. Say I walk into the studio and go, hey, brother, what's happening? Now, the man knows I'm saying, how are you? How's the family? How are you in general? Now, that's functions, man. Get it? Now, see, the only trouble is, on the SATs, they don't use F for function, man. No, they use all these strange little signs, like a dollar sign, or an ampersand. One of them little things with a line like this, and a line like this, and a line like this, about that big. You know, whatever they call those things. That's why we call them funky functions. Now, I'll show you how it's done. Now, here's the problem for you. Let's see what you can do. Say the dollar sign x means x squared plus 2. Now, take the dollar sign 8 and figure out the value, but don't you hesitate, because then I'll have to tell you, you take 8 and square it. That'll give you 64. To get the answer I swear, just add 2 more. Now, 64 plus 2 will give you 66. I told you it was easy, just like picking up sticks.
Well, that's it for Math Aid. I hope you've enjoyed our program, and I'd like to thank my very special co-host, Johnny B. Squared.
Well, Jimmy, it was a real pleasure to be here. When in Rome, do as Romans do. I'd like to leave you with a little quote that my Uncle Pythagoras used to say to me as he tucked me into bed every night. He'd come over to the bed and look me square in the eye, and he'd say, Johnny, in life, there are many variables. In life, there are many inequalities. And you can be square, and you can be radical, but always be you.
Thank you, Johnny B.
Good night, everybody.
Good night.
What do I do with these fractions? I can't figure this equation out. The numbers...
Good evening. I'm Ted Topical, and this is Mathline. As everyone knows, the latest controversy in the nation's capital centers around the Pentagon. It appears that in a fit of peacetime boredom, a group of Navy admirals is lobbying to change the shape of the Pentagon. Most Army and Marine Corps brass is bitterly opposed to the idea. With us now in our Washington bureau is Admiral Puget Seawash, a proponent of the idea. We'll also be talking to Army General Harlan Foxhull Hardwater. You first, Admiral Seawash. What can you possibly gain by changing the shape of the Pentagon?
Well, I'll answer that in one word, Ted. Area. We need more office space. We also feel that a pentagon is an outmoded, definitely unship-shaped shape.
General Hardwater?
Well, you're full of bilge, Admiral. The Pentagon is perfect as it is. 5 equal sides representing the 5 branches of the military. Army, Navy, Air Force, Marines, and Rambo. And it has plenty of area. I don't suppose you've taken the time to figure that out, have you? Of course not, so listen closely. We know each side of the Pentagon is 60 yards long, and the distance from the midpoint of each side to the center is 40 yards. So we can divide the Pentagon into 5 equal triangles, each with a base of 60 yards and an altitude of 40 yards. So, the area of a triangle is 1/2 the base times the altitude, in this case, 1/2 60 times 40, and that gives us 1,200 square yards. Multiply that by 5 for the number of triangles in the shape, and you have 6,000 square yards filled with office space, cafeterias, the little general's room, a nice boutique.
But General, isn't it common knowledge that Rambo, as the most effective military branch, has already taken over more than half that space?
Ha, that's right, Ted. And the Navy has a solution to our space snafu. On the same land, we can erect a triangular building. We propose a right triangle with a base of 50 yards, providing ample VIP parking, and an altitude of 120 yards, giving us more than enough wall space for the Colonel's annual handball tournament.
That's all well and good, General, but what about the third side?
No problem, Ted. As we all know, the side opposite the right angle is called the hypotenuse. The formula for determining its length is a squared plus b squared equals c squared. In our proposed building, that would be 50 squared, 2,500, plus 120 squared, or 14,400, equals 16,900. The square root of 16,900 is 130. That's 130 yards of available window space looking directly over the Potomac.
Isn't there any easier way to find the hypotenuse?
Well, that formula, a squared plus b squared equals c squared, will work to find any side on any triangle if you remember that c is the hypotenuse. But it so happens that my right triangle has side measurements that are multiples of one of the common Pythagorean triples. Those are sets of 3 numbers that fit the Pythagorean theory. You can avoid all that squaring and multiplying and square rooting. As I said, mine was 50, 120, 130, though it's better to remember 5, 12, 13. The others are 3, 4, 5, 8, 15, 17, and of course my favorite, 7, 24, 25. Take them on sea trials. In the 3, 4, 5 right triangle, for example, 3 squared, 9, plus 4 squared, 16, equals 5 squared, 25.
Admiral, you're getting away from the issue. What do you gain by replacing the Pentagon with your triangle?
Now, again, the area of a triangle is 1/2 base times altitude. So my triangular building would have 3,000 square yards of area.
Aha, you waterlogged old case of kelp. You've cut the area in half.
Ha! You hunk of moss! We build them 3 or even 4 stories high, and add 3,000 square yards each story. Give Rambo the top floor and a parachute, huh?
Gentlemen, you're both out of line.
I'm betting your hatches.
When we come back, we'll examine reports out of Dead Bird National Observatory where astronomers claim to have found a new constellation. Now this.
Hi. I just moved in next door. Could I borrow a Diet Pepsi?
Sure. Come in. Yes. How about something else?
Listen, if you don't have a Diet Pepsi...
No, I got it. Headed up to heaven, chasing down a dream. Turning up my engine, attention screen. I'm on the edge tonight.
You okay in there?
Here's your Diet Pepsi.
That must be my roommate, Danny.
Danny?
Hi, I'm Danielle. You got another Diet Pepsi?
Sure.
Diet Pepsi, the choice of a new generation.
Since recorded history, man has been speculating about our place in the universe. Are we alone? Is there life out there in the cosmos? And it seems there has been a lot of activity on that frontier. A rash of UFO sightings, the discovery of a new constellation, even a theory that alien beings landed here thousands of years ago. With us tonight to explore these issues are Dr. Elmer van der Van, self-proclaimed expert on extraterrestrial life, and Dr. Carlos Sagacious, the very wise and renowned astronomer. Dr. van der Van, let us start with you. Your claim that this geometric configuration, which looks like two parallel lines intersected by a third line, is proof that alien beings came to our planet many years ago.
Yes. Actually, yes. A student of mine sent me this photograph taken from a plane flying high above Princeton, New Jersey. Now, if you look at the enlargement, you will see all those little letters A, B, C, D, E, and so on and so forth, and so.
And how does this prove your claim, Dr. van der Van?
Well, look. See, I measured the angles formed at the points where the lines intersect, and guess what? Just like in real life here on Earth, when you have two parallel lines intersected at a third line at an angle, the alternate interior angles are equal. Here, see, angles D and F are equal, also angles C and E are equal. I measured it and found that angle D is 60 degrees, and angle F is 60 degrees, and C is 120 degrees, so is E. It's very, very nice angle.
Yes, just as one would expect of geometry. But what does this have to do with aliens?
Oh, well, also we know that the corresponding angles, angles B and F, should be equal, and they are. Yes! And the same thing goes for angles A and E.
Excuse me, Dr. van der Van, if I may interrupt you, but so far you proved only that you are familiar with the angle relationships in parallel lines intersected by a third line. Commendable, certainly, but hardly evidence of visitors from another planet.
Well, yes, actually, but let me finish. There's more, you see. These angles A and B together should equal 180 degrees, and they do. 60 plus 120 degrees equals 180 degrees. And these guys, too, angles C and D equal 180. Also E and F and H and G. What symmetry?
Yes, we can see that, but I'm afraid your point is lost on me, sir. Perhaps Dr. Sagacious can illuminate this for us.
Well, Ted, Dr. van der Van has been a rather fascinating character, but once again, his theory is billions of light years off the mark. It is quite clear that this aerial photograph is of two roads intersected by a third. The little letters clearly have been added.
But, my dear colleague, look at the close-up of the photograph. See there in the right corner? It says ETS, SAT, headquarters. That can only mean extraterrestrial station. SAT can only mean space alien troops. Headquarters, absolute proof.
Ah, my good friend, what a wonderfully imaginative interpretation. But I'm afraid the explanation is far simpler. ETS means Educational Testing Service, the people who make up the SAT, the Scholastic Aptitude Test. They are located in Princeton, New Jersey.
And you have our gratitude, Dr. Sagacious, for clearing up that mystery. And you, Dr. Vondervan, must be thanked for providing high school students with a few pointers they can keep in mind when taking the SAT. And now, Dr. Sagacious, I understand you have made a startling new discovery.
Well, yes, Ted, that's right. While studying the cosmos, it's often very difficult to isolate constellations from the billions and billions of stars up there. Take a look at this star field.
It looks like, well, billions and billions of stars.
Billions and billions. But hidden in these billions and billions of stars is a new constellation. The trick is to find it.
And I gather, sir, that you're going to show us how.
Yes. Let us superimpose this grid on the star field. Notice the x-axis, the horizontal line, and the y-axis, the vertical line. Now we are prepared to plot the locations of the stars in our new constellation. The first star is located at point 4, 3. The second is at 4, -3. The third at 0, -1. The next at -4, -3. The next at -4, 3. And the final one at 0, 1. Now, all we have to do is connect the dots.
And you have a constellation that bears a striking resemblance to a bow tie.
In my interpretation, I would call it a butterfly.
Whichever it is, gentlemen, I'm not sure I understand just how you plotted those points. I'm afraid my knowledge of astronomy is limited.
Actually, Ted, all it takes to understand this is a little knowledge of geometry. Remember that coordinate geometry provides us with a way to plot points. These points, as we have seen in our constellation, are expressed in terms of their position on the x and y axis. For example, the star at point 4, 3 is located 4 points from 0, which is called the origin, on the x-axis, and 3 points from 0 on the y-axis. The star at point 0, -1 is at 0 on the x-axis and -1 on the y-axis. Dr. Vondervan, you seem to know geometry. Perhaps you can help us locate a lost star.
Yes, actually, I'm very good at finding things.
Good. Now here we have the coordinates of 2 very, very bright stars, easy to see in our star field.
Yes, I see.
These stars are located at points 0, 0 and 12, 8. A third, much weaker star falls directly between these 2 stars.
That would mean that it falls on the same line segment.
Quite correct. But we have mixed up the data on the coordinates. However, we have these choices. A, 2, 3, B, 2, 4, C, 3, 2, D, 3, 4, and E, 4, 2. Which is the correct one?
Yes, easy as pie. A little geometry joke. Pie, get it?
Yes, most amusing. Now, can you find our lost star?
Oh, yes. Actually, it's right there at 3, 2. That's choice C. Now, that's because you know that a point on a line segment will have the same ratio as another point on the same line segment. Point 32 is the same ratio as point 12, 8.
Excellent, Dr. Vondervan. You've found our little lost star.
Oh, and it looks so happy, too.
Thank you, Dr. Vondervan, and thank you, Dr. Sagacious. This is Ted Topical for Mathline. Good night.
Sports fans, and welcome to another chapter of SAT Sports Roundup, the only sports program dedicated to the proposition that athletics and scholastics do mix.
That's right, Frank. You know, most kids love sports, whether they watch or play. But few realize that all around them are hundreds of SAT math section problems in the making.
But, as we prove each week, there are an infinite number of math problems to be uncovered in every contest. And all the different kinds of problems you'll find on the SAT. Word problems, problems that test your arithmetic skills, your algebra ability, and your command of geometry. But before we see what problems presented themselves this week, let's review our SAT math problem-solving strategies.
The very first thing you do is be sure you understand the problem. Read it carefully to be sure you know what you are being asked to solve or find out. A quick look at the answer choices will help you determine this. Are you looking for a percentage, a fraction, a decimal, a dollar value, an algebraic expression, the area or volume of something?
That's right, Chrissy. Now go over that problem again to see what shortcuts you can use. Remember, the SAT math is not a test of your ability to do long, involved calculations, but rather a test of your ability to make logical decisions. So, look to see if you should, for example, convert a word problem into an equation to find the answer quickly. Or substitute numerical values for the variables, or just plug in each answer to find the one that works.
Look for answers you can easily eliminate from your consideration and cross them off. Which answers are obviously wrong? Which ones appear too easy? Perhaps they're to trick you.
Work out the problem using the shortest route possible. And when you find your answer, either directly or by process of elimination, look for the connection to the problem to be sure that it makes sense.
If you can't find the way to attack the problem, make a mark next to it and go on. Go back to it later if you have time.
Now that we've got our strategies down, let's see how we do on this week's math problems in sports. And as we solve these problems here in the studio, we want you kids at home to work them out as well.
Well, Frank, our first couple of problems come to us from football. Here he is, the icebox, big fella. Now, he weighs 7/5 the weight of the quarterback. The quarterback weighs 5/6 the weight of the linebacker, who weighs 212 pounds. How much does the icebox weigh?
Gee, that's a tough one, Chris. What are the choices?
A, 176 2/3 pounds. B, 295 4/5 pounds. C, 247 1/3 pounds. D, 230 pounds. E, 255 pounds.
Well, Chrissy, I'm going to eliminate A because that just doesn't seem high enough. Heck, that's less than I weigh. But all the other choices do seem possible, so I guess it's time that we do some figuring.
Well, you might start by noting that the quarterback, QB for short, weighs 5/6 times 212, the weight of the linebacker. So, to find out how much the icebox weighs, we make an expression like this. 7/5 times 5/6 times 212 over 1. Now we can show this as a fraction like this. So we have 7 times 5 times 212 over 5 times 6 times 1. Then we cancel the 5 on the top of the fraction and the 5 on the bottom, and that leaves us with 7 times 212 over 6.
Well, then I guess you just multiply 7 by 212 and divide by 6. Let's see. 7 times 212 is 1,484. And 1,484 divided by 6. Let's see, that gives you 240.
At this time, you can stop figuring, Frank, because the one answer that fits is C, 247 1/3 pounds.
Good point, Chrissy. Now, time out for an SAT tip. Always save time whenever you can. Keep in mind that the correct answer is right there in front of you.
The next problem takes place behind the scenes before the game. For the Banana Bowl, 1,000 seats are priced at $10 per ticket. 1,500 seats are priced at $25 per ticket. and 1,000 seats are priced at $50 per ticket.
Wow!
If 87% of the total number of seats is sold, how much money is realized at the game?
Well, that sounds pretty easy, but maybe there's a trick.
One never knows.
Do one.
Okay, the choices are A, 107,500. B, 1,075,000. C, 258,825. D, 93,525. E, cannot be determined from the information given.
We're looking for the amount of money made if 87% of the seats were sold. Well, at a first glance, this looks like a simple percentage problem. So first we have to find the total number of seats. Well, that's 3,500. And then we take 87% of that, which is, well, let's see, 87 over 100 times 3,500 over 1.
Frank!
Now, let's see. We cancel out the 2 zeros in the numerator and the denominator over here.
Frank!
And that leaves 87 times 35.
Frank!
I hate multiplying these.
Frank! You don't have to, Frank. Frank, stop.
I am not finished calculating this, Chrissy.
Frank, if all 87% of the seats at the banana bowl were filled with monkeys, they'd have figured out this problem by now.
Well, there's no way to answer this, Chrissy.
Exactly, Frank. And that's why the correct choice is E, cannot be determined from the information given. Do you know why?
Well, because you can't tell what percentage of each type of ticket was sold.
Yeah, but you were fooled into doing what you started to do. Add up all the seats to get 3,500, take 87% of that. Then I suppose you were going to multiply the sum of all the prices or something.
I had no idea what to do next.
You forgot the strategies. Look, Frank, look for the shortcuts. Remember, look at the answers. You just jumped in and started doing calculations without thinking.
Well, you're right, Chrissy. To tell you the truth, I was really just trying to figure out what kind of money we were talking about here.
Time out, another tip. Don't let your mind wander during the test. Don't get sidetracked by something else. Like, what kind of career you're going to have after going to college. You've got to get to college first.
Thanks for reminding us, Chrissy. Now let's turn to another sport for some different kinds of problems. For this one, we're going to roll the tape.
We're on the 18th green. This putt means the match for one of these two fine golfers, birdie par and bogey sand wedge. Let's look at the lie of these two putts. Oh, it's very close.
Hidden in the drama of this golf match is a geometry problem. Let's say we draw a triangle formed by the pin and the two golf balls. Now, in this problem, we'll say that the figure is not drawn to scale. You'll see that sometimes in this test. Let's say we know the angle at the lines intersecting Bogey's golf ball is 90 degrees. That Birdie has a putt of 25 feet, and the distance between the two balls is 7 feet. How long is Bogey's putt? Here are the answer choices. A, 25 feet. B, 32 feet. C, 87.5 feet. D, 24 feet. E, 17 feet.
This one is a very easy one, Chrissy. What we have to remember is that we're working with a right triangle. And so we can apply the Pythagorean theorem, a squared plus b squared equals c squared, side c being the hypotenuse. Let's plug in the numbers we know. A equals 7 and c equals 25. So we have 7 squared plus b squared equals 25 squared. This becomes 49 plus b squared equals 625, or b squared equals 625 minus 49, which equals 576. Now we find the square root of 576, and we have our answer.
At this point, it might help to look at the answers. Eliminate those we know won't work, and plug in the ones we think might work. We know 25 won't work, because the side can't equal the hypotenuse. Nor will 32 or 87.5, because certainly the side can't be longer than the hypotenuse.
That leaves choices D and E. Let's try 24 first.
And that's the answer. 24 squared is 576.
There are two other shortcuts to make this solution become apparent even more quickly. Since we're looking for a number that equals 576 when squared, we know that it must be an even number. That means we can also eliminate E, 17 feet, without having to calculate. But the shortest shortcut of all is to recall the common Pythagorean triples. Sets of three numbers that fit the a square plus b square equals c square equation. These should be memorized. 3, 4, 5. 5, 12, 13. 8, 15, 17.
And then there's my favorite, 7, 24, 25. Well, that's a good tip, Chrissy. And if you knew those, you'd be able to spot the right answer almost immediately. Well, Chrissy, now it's time to take me out to the ball game and buy me some peanuts and Cracker Jacks.
Actually, we're talking hot dogs here, Frank. You know, those hot dog vendors really work hard, but they never get any glory. So, we're here to honor them.
Listen to the problem. Vinny the hot dog vendor buys hot dogs at 97 cents a dozen and buns at 41 cents a dozen. If he sells the hot dogs at $1.25 each, what is the total profit on 7.5 dozen hot dogs?
Now, this could be one of those sneaky questions. What about the cost of mustard?
Doesn't say anything in my script about mustard, Chrissy. Just hot dogs and buns. All right, here are your answer choices. A, $87.30. B, $77.63. C, $102.15. D, $112.50. And E, $124.20.
Well, Frank, the first thing I'd do is calculate the total amount he makes selling
7.5 dozen hot dogs
at $1.25 to see if I could eliminate some answers. Multiplying the numbers gives me $112.50. So right away I can eliminate D because that's the total amount taken in before subtracting the cost of the hot dogs.
And you can eliminate E because that's even more than the gross total. So now you add 97 and 41 cents to get $1.38, which is Vinny's cost per dozen. Multiply that times 7.5, which gives you $10.35. You then subtract that from the total amount Vinny took in, and that would...
You can see without doing the subtraction that the only possible choice is C.
Well, once again, thank you, Chrissy, for saving me that last tedious step.
Don't mention it, Frank. Now, here's a problem from a sport that requires a special kind of skill. Pool. On a pool table, there are 15 balls, each labeled with a different integer from 1 to 15 inclusive. If 3 even-numbered balls are removed, what fraction of the remaining balls are even-numbered? A, 4/7, B, 1/2, C, 5/12, D, 1/3, E, 1/4.
The first thing you have to determine is how many balls are even-numbered. If there are 15 balls total, then 7 must be even-numbered. Take 3 balls away, and that leaves 4 even-numbered balls.
So, the answer must be A, 4/7.
Ah, not so fast, Chrissy. You must not have been listening to yourself as you read that question. It said what fraction of remaining balls are even-numbered. That includes the remaining odd-numbered balls, too.
Oh, right you are. So you have 12 balls remaining, 4 of which are even. 4 over 12 is 1/3. Answer D.
That's right, Chrissy.
Well, moving right along to my favorite sport, basketball.
The Western Basketball League logo is a basketball in a square. If the logo shown on the scoreboard is 4 feet on a side, what is the area left remaining in the box after subtracting the area of the basketball? And here are the answer choices. A, 3.14, B, 34.24, C, 3.44, D, 4.0, or E, 12.56.
Uh-oh. This is one of those geometry problems where you have to remember how to get the area of a square and a circle. Now, the square is easy. Its area equals the side squared. That's 16. The area of the circle, I forget.
Why, Chrissy, I'm shocked. You should know this stuff cold to save time. But if you do forget, it's right at the top of the test section under the directions. Area equals pi r squared. R stands for radius.
And what's the radius?
The radius is half the diameter.
And if it's half the diameter, how do I know what the diameter is? It's the same as the side of the square.
Because the circle is inscribed in the square.
Oh, right. Now, if r is 2, then r squared is 4. So the area is 4 pi. Do I have to do the multiplication?
Oh, Chrissy, the answers are given without pi, so I guess so. 4 times 3.14. You still have to subtract the area of the circle from the area of the square. Here, I've done the calculation for you. It's 16 minus 12.56, which equals 3.44.
Ah, answer C. I was going to say it was 16 minus 4 pi, then divide 4 into 16 to get pi as the answer.
And you would have been wrong.
All right, all right, all right. I'm still ahead of you, Frank, so let's just move on to the next one, huh?
Okay, don't get testy.
Why not? We're talking about a test, aren't we?
Points off for bad puns. Okay, let's move on. Here's one of my favorite kinds of problems. Players A, B, C, D, and E make up the starting offense on the Brooklyn Bluebirds. Player A is taller than player C. Player B is not as tall as at least one other player, and not as short as at least one other player. Player D is the tallest. E is taller than all but 2 other players. Which player is the shortest? And here are the answer choices. A, B, B, C, C, D, E. E cannot be determined from the information given.
Well, I guess the way to approach this is to make a line with the left side representing the shortest player and the right side representing the tallest player. Now, D we know is tallest, so we put D at the right. E is in the middle. He's taller than all but 2 other players.
We also know that A is taller than C, so we can put C to the left of A. B is also somewhere in the middle, either between E and D or between the shortest and E. So, by the process of elimination, we can determine that the shortest player is C.
Ready for the next problem? Here's one about marathon running.
Ooh.
Steve ran the 26-mile marathon in 3 hours. In the first hour, he covered twice as much distance as he did in the second hour, and 3 times as much distance as he did in the third hour. Now, how far did he get in the first hour? A, 14.18 miles, B, 10.0 miles, C, 15.60 miles, D, 18.14 miles, and E, 13.0 miles.
Oh, boy. I think I'd rather run the marathon and try to figure this one out. Where can we begin?
Well, this is one of those motion problems. We're trying to find out how many miles Steve ran in the first hour. Let's let X represent the variable that we're looking for, the number of miles he ran in the first hour. So, he ran half that in the second hour. That's 1/2 times X. And 1/3 that in the third hour. That's 1/3 times X.
So we can say that X plus 1/2 X plus 1/3 X equals 26 miles. Let's show it this way. Whoa! How do we deal with those fractions?
Find the lowest common denominator, which is 6. Then multiply everything by 6. That gives us 6x plus 3x plus 2x equals 156. Now we can add to get 11x equals 156. Then divide 11 into 156 to get 14.18.
And the answers are rounded off to the nearest hundredths.
You know, as we watch all those games, we never really think about how much all those uniforms cost.
Or how they get paid for. To finance the uniforms of this hockey team, the manager borrowed $10,000 for a year. The cost of the loan was 9% of the amount borrowed to be paid back together with the loan at the end of the year. What was the total amount needed to pay off the loan? A, $10,009. B, $10,090. C, $10,900. D, $19,000. Or E, $90,000.
This should be an easy one, as long as you remember what, home viewers?
Where to put the decimal point after you multiply 10,000 times 9%. The key is to remember that the cost of the loan is 9% times 10,000. That's 0.09 times 10,000, or $900. Then you have to add the 900 to the 10,000, and again, be careful where you put the zeros. So, what's the answer? If you said C, then you're absolutely correct. Well, Christy, that about wraps up another SAT Sports Roundup.
Yes, Frank. And now remember, sports fans,
Scholastics and athletics do mix. Good luck on your SATs.
Bye-bye now.
Excuse me, Mr. Looseleaf?
Oh, hi, Larry.
Hi.
All set for the SATs?
Well, I still don't understand those qualitative comparisons.
Quantitative comparisons, Larry. Watch my lips here. Quantitative
All right, the
comparisons.
quantitative comparisons, that's right. See, I missed the class where you reviewed that part of the test. Do you think you have time to go over it right now?
Sure, Larry. Have a seat there.
Great.
Yeah, well, you know that the quantitative comparisons are the part on the math section of the SAT where you compare two quantities, one in column A and one in column B. And you have to decide whether the value in column A is greater than the value in column B, or whether the value in column B is greater than the value in column A, or if they are equal, or if there isn't enough information to tell. See this example? Notice that there is an expression under column A, 2 times 6. Under column B, the expression is 2 plus 6. Okay, now, for these questions, you're supposed to answer in every case as follows. Mark A if the quantity in column A is greater than the quantity in column B. Mark B if the quantity in column B is greater than that in column A. Mark C if the two quantities are equal. Mark D if the relationship between the two quantities cannot be determined from the information given. Is that clear?
What do you do with E?
On quantitative comparison questions, you leave E absolutely alone. You mark it, it won't be scored. That is, you'll get no credit.
Okay.
So, Larry, which column contains the greater amount, A or B?
Well, that's a quick trick question. What if it's C or D?
Okay, Larry. What is the answer? A, B, C, or D?
Well, that's an easy one. Column A, because 12 is greater than 8.
Correct. You would mark answer A. Now, do you get the gist of this?
Yeah, it looks easy.
All right. Quantitative comparisons look easy, but as you know, Larry, looks can be deceiving. As you'll discover, some of these comparisons get really tricky. But not to worry, you'll learn just how to handle them. Now, we'll do some quantitative comparison questions on this page here. We'll do it like this. I'll give you problems and you work them out, all right?
Okay.
Then I'll ask you to tell me why you picked the answer that you picked. This way, you'll learn some of the special strategies for answering quantitative comparisons. Understand? All right. We'll do practice round. First problem. You decide. Is X greater than Y? Is Y greater than X? Or can't you tell?
Well, I think the answer is C.
Why?
Well, because the information given states that side AB is equal to side BC, and then we know that the angles opposite side AB and BC are equal. So X equals Y. So the answer has to be C.
Great! That means you remembered the rule about triangles. All right. Here's the next problem. Let's try a harder one. All right, the information given is this triangle with a 45-degree angle at the top and the two other angles represented by X degrees and Y degrees. Note the information given below the triangle. Okay, the question asks you to compare angle Y to the numerical value 90. Okay, Larry, what did you decide?
Well, I don't know. This one seems stupid to me. I really got confused because it said that X is less than 45 and that Y is greater than 45, right?
Yes, that's what this note under the triangle means.
Well, even if Y is greater than 45, it doesn't look like it could be more than 90 degrees, so I chose B.
But it says not drawn to scale. So it doesn't matter what it looks like.
I know, that's why it's confusing.
Okay, here's how to figure it out. First, you have to ignore the scale of the drawing so you don't get confused. You know that all three angles of a triangle add up to 180 degrees. So you can say that x plus y plus 45 equals 180 degrees. And you know that x plus y equals 135 degrees. And since it says that x is less than 45, it has to be that y is greater than 90. Say, for example, that x is 44. 135 minus 44 is 91.
Oh, I see, Mr. Looseleaf. You just have to know your rules about triangles.
And you have to pay attention to the information that's given. Be sure to note if the drawing is to scale or not. All right, here's the next problem. So here you're asked to compare x and y. Don't tell me your answer yet. And here's a little hint. The tougher the questions, the less likely the answer is going to be D. That's kind of a cop-out answer for people who can't figure out how to approach it. What about C? That's the answer you picked.
Well, if you draw lines between each point, the lines TS, TP, etc., are all equal. Then all the triangles are equal in area, like equilateral triangles. So the sides must all be equal, and that makes the angles all equal, right?
Wrong. Sorry, Larry. But you made a leap from the idea that all triangles are equal in area to the idea that they must be equilateral triangles. Not so. You can have 5 triangles that are all the same area, but which do not have 3 equal sides. Review your geometry.
Well, what about answer A? Is it A?
Let's see. Work through the problem.
Well, you know that angle Y must be 1/5 of 360 degrees, since there are 360 degrees in a circle, and 5 equal triangles. Angle Y is 72 degrees, then you subtract 72 from 180 degrees, since you know there are 180 degrees in a triangle, and you get 108 degrees, which is greater than 72 degrees, and, I forgot one more step.
Yeah, you forgot to divide 108 by 2. There are 2 equal angles remaining in the triangle. So the answer is B. Y, which is 72 degrees, is greater than X, which is 54 degrees. You had the reasoning all right, but again, you just made a careless error. If you can conquer that bad habit, you'll do great.
I know, I just get so nervous.
It'll help you if you keep reminding yourself that you really do know this stuff. And the more you practice doing these problems to get the hang of it, the less you'll worry about it. That way you can concentrate on what you're doing and avoid making costly, careless errors. Larry, if you think you need some practice with these geometry problems, be sure you review and practice. The next few problems will test your algebra skills. Here we go. We get no extra information, just these 2 expressions. This is an easy one, right, Larry?
Well, it seems obvious. I mean, 2x must be greater than x. So wouldn't 2x plus 1 be greater than x plus 1?
The question is, what is the value of x?
Oh, well, maybe it could be 0. So 2x plus 1 equals 1, and so does x plus 1 equal 1. Therefore, C could be the answer.
Could be the answer if x equals 0. But what if x equals -1?
Oh, right. So if x equals -1, then column A would be greater. -1 plus 1 equals 0. -2 plus 1 equals -1.
Okay, I'll explain why the answer could only be D. The point is, you do not know if x equals a positive number, or 0, or a negative number. You don't have enough information, so the answer has to be D. There's a lesson to be learned from this example. When doing quantitative comparisons, especially when you are asked to compare variables, you should consider all the possibilities. Don't jump at the obvious conclusion. Ready for the next example?
Yep.
Okay. I'll give you a few seconds to figure this out. First, let's consider answer D. We just had the same kind of problem. So x could be anything except for 1. So would that still mean that you didn't have enough information?
I don't agree with that answer. I picked answer A. I tried substituting 0, -1, and +2, and each time the value in the column A was always greater than x.
Good. You remember to try all the possibilities. Here's another way to figure it out. You factor the expression x squared minus 1 and simplify the fraction in column A. You know that x plus 1 would always be greater than x, no matter what the value of x.
Oh, factoring, I forgot about that.
Well, now you'll remember it when you're taking the test. Here's a problem that's strict numbers.
Forget it, that's impossible.
Hey, this is an easy one. Obviously, the answer can't be D.
Oh, and why not?
Because even if no one in this class could get it, someone could. It's just numbers.
But it would take a person forever to figure that one out, and you're not supposed to have to do long calculations on the SAT.
That's right. Usually there's a shortcut to finding the answer or on problems like this. Always look for the shortcut. Now you can figure it out.
Ah, yeah. You just cancel out the terms that are the same in both columns. So you end up with 45 in column A and 46 in column B, so the answer is B.
Good, Larry. I repeat, always look for the shortcut. And now, one more for the road, an easy one. This one shouldn't take you long. All right, Larry.
Well, they're both the same. They both add up to -10.
You added up all the numbers, but you forgot one little thing. Try again and remember the little song.
Oh, yeah, and Sally. You have to do the calculations in the parentheses before you do anything else. So A ends up being 12 and B is 0.
Good work, Larry. Don't forget all the tips and strategies you've learned. And don't forget to, please, excuse my dear Aunt Sally.
I won't, Mr. Loosely. And thanks a lot.
All right, you're welcome. Get out of here, huh?